Last week, we began our discussion of L'Hopital's rule, and we saw that we could use the derivative to compute certain limits. In particular, we used it to compute limits which took a form of 0 over 0 upon substitution, or infinity over infinity, positive or negative. Here, we're going to see how we can use L'Hopital's rule to compute limits which take any of these four forms: 0 times infinity, 1 to the infinity, infinity to the 0, 0 to the 0. These last three are sometimes called indeterminate forms. Yeah, I'm not going to use that word. That's an unnecessarily large word to use here. But we're going to see, we're going to see three of these. The last three, the way you go through the computation is similar for all three. So we'll do one example of the first form and two examples of those last three. But we're not going to have a new L'Hopital's rule, a second L'Hopital's rule. We're still using the same L'Hopital's rule. But what we're going to do is use some algebra to make limits which take these forms look like a 0 over 0 or an infinity over infinity. So let's see that with this example. Limit as x approaches 0 from the right of x times the natural log of x. On the right of 0, because natural logs require a positive number inside their domain. So this limit right here, if you do a direct substitution, you'll notice, where should I write this? Let's see. So I'm going to go across the board to do this example. But down here, I'll write what happens on direct substitution. Now this first one, 0 times infinity. Infinity could be positive or negative. Here we have a 0 times a negative infinity. As x approaches 0 from the right, x goes to 0, and log x goes to negative infinity because the graph of log x looks like that. So as x goes to 0 from the right, that goes down to negative infinity. So right here we have a 0 times a negative infinity. L'Hopital's rule does not apply to a limit of that form. But what we can do is take this 0, or take the infinity. Here, we'll take the 0. It's easier algebraically. But we can take this 0 and throw it in the denominator. And what will that do? Well, what's making this 0? This x is making that 0. So let's throw that in the denominator. How can we do that? Well, an x in the numerator is the same as a 1 over x in the denominator. Because right here, this fraction simplifies to that equation. Well, it's not an equation. It simplifies to this expression. If you, multiply by the reciprocal, you can see that those are equal, because the reciprocal of 1 over x is x. So right here, this equal sign is valid. What we did is take this x and put it in the denominator. Now, why would we do that? Well, let's look at the form that this takes. As x goes to 0 from the right, log x goes to negative infinity again. The denominator, the 1 over x, now goes to positive infinity as x goes to 0 from the right. Why is that? Well, 1 over x, one of our basic graphs from the beginning, looks like that. As x goes to 0 from the right, that goes to positive infinity. And right now, this is in a form on which L'Hopital's rule applies. So we took this 0 and threw it in the denominator. So you could have taken the infinity and put it in the denominator. But here, having an inverted log x, taking that derivative would be kind of a pain. So here, I'm just going to put the 0 in the denominator and make it an infinity over infinity. If you put an infinity in the denominator, it would be a 0 over 0, and L'Hopital's rule would still apply. But here, L'Hopital's rule applies to this, so we're going to use L'Hopital's rule. I wrote down there infinity over infinity with a negative sign. So that limit now equals this limit. Derivative of the top, 1 1 over x. Derivative of the bottom, here's one of those cases where jumping straight from 1 over x to its derivative, negative 1 over x squared, is, I think, more convenient. Because now we're going to have to simplify this, because right now it's not clear what this limit is. And how does this simplify? It's still a limit as x goes to 0 from the right. It's the limit of negative x. Because what, this 1 over x times negative x squared just leaves you with 1x and a negative sign. And as x goes to 0, that goes to 0. So what we did here, we took a 0 times an infinity, converted it into a form on which L'Hopital's rule applies, and then we applied L'Hopital's rule. Now, we did that for a 0 times an infinity. What about these other three forms? These are 1 to the infinity, infinity to the 0, 0 to the 0 forms. How can we do that? Well, I'm going to erase this, so I'm going to continue writing under this remark. Remark. The following equal signs indicate symbol manipulation. Meaning, in the limit, they are equal, but if I threw limits on everything, it would look much more confusing than it would if I don't throw limits on everything. So I'm just going to say that these are all symbol manipulation. And they're to illustrate how we can turn one of these three into a form on which L'Hopital's rule applies. So, first, 1 to the infinity. Now, the 3 bullet points, 1 for each one. 1 to the infinity, well, we have a number and an exponent. Exponents are, well, L'Hopital's rule doesn't apply to exponential functions. But what we can do is throw a logarithm on that. How does that help? Well, you throw a logarithm on it, symbol manipulation, the infinity comes out front, so you have infinity log 1. Well, that's great. What's log 1? Well, that graph over there goes through the point 1, 0. So that's an infinity times 0 form. And then L'Hopital's rule applies to that as in the first example. And with symbol manipulation, I'll just say that we can make this equal to an infinity over infinity, or 0 over 0. But see, if we throw a logarithm on our 1 to the infinity form, you can bring the exponent down, and then that turns into a 0 times infinity form. What about the others? Well, we're again going to use logarithms. Infinity to the 0 form. Well, again, the 0 comes out front. You have 0 log infinity. As x goes to infinity, where does log x go? Well, that arrow's not completely following it. But that is still increasing without bound. So we have here a 0 times infinity, and L'Hopital's rule applies there if we convert that into an infinity over an infinity. And I will say, or 0 over 0 for both of these first ones, depending on which thing you throw in the denominator. And that would depend on which derivative you'd rather take. And again, this one I'd rather take the derivative of 1 over x than the derivative of 1 over log x, because that would require a chain rule argument. What about this last one? Or quotient rule, I guess. 0 to the 0. What happens with 0 to the 0? Throw a logarithm on it. You get 0 log 0. Now again, log 0 doesn't exist. But here, in the appropriate limit, we're going to look at 0 from the right. And that becomes a 0 times a negative infinity. And we saw in that first example how a 0 times a negative infinity becomes, or can become, an infinity over infinity, or 0 over 0. And in all of these last parts, L'Hopital's rule does apply to limits which take those forms. So let's look at two examples. I have like a dozen examples written down here, but some of them are... I will put one or two other examples up on Canvas so you can see how some of the computations can get. But let's look at these two. I need my eraser to do that. Erasing that well. So let's look at two examples. Limit as x approaches 0 from the right of x to the x. So right here you try a substitution, you get a 0 to the 0. And we can see by that last line down there that if we throw a logarithm on that, we can make it look like an infinity over infinity, or 0 over 0. So let's do that. But notice, if we throw a logarithm on that, that is a new function. Well, a new limit that we're taking. So I'm going to write up here equals with a star. And the star is going to be the side work with the logarithm on it. So star, we compute. What are we computing? We're computing this limit. Limit as x goes to 0 from the right of log x to the x. A new function, but one we can take the limit of, and then we can get rid of the logarithm by taking an exponential. And we'll see that in a moment. So what do we get here? Well, we can see why we need 0 from the right, because we are going to use a logarithm. If we had just limit as x goes to 0, limit wouldn't exist by a domain restriction. But from the right, logarithm is defined. So we have here, this equals limit of x log x as x goes to 0. And how do we do this limit? Is this the same one we had? Oh yeah, it is the same one we had. I didn't notice that. Huh. Well, how would we do this? Well, again, I'll go through the work. This isn't the same as the first example. But what we have here is a 0 times an infinity. A negative infinity. We're in this step, so we have to make it look like a form on which L'Hopital's rule applies. So equals this limit. Log x, put the x in the denominator, that makes it a 1 over x in the denominator. Now it is an infinity over an infinity, a negative infinity over a positive infinity. L'Hopital's rule applies, so that limit is now equal to this limit. Derivative of the top, 1 over x. Derivative of the bottom, negative 1 over x squared. This simplifies to the limit. We still haven't taken the limit yet. X goes to 0 from the right of negative x, and that equals 0. Well, isn't that great? We found a limit. But notice, that isn't the limit we wanted to find. We wanted to find the limit of x to the x as x goes to 0. We have the limit as the logarithm of that, as x goes to 0 from the right. Well, how can we use what we found to find what we want? Well, we can get rid of the logarithm. This logarithm is in the way. How do we get rid of a logarithm? With an exponential. The exponential is a continuous function, so you can throw it inside limits. So here, take the exponential of everything down here, and that tells us e to this limit equals e to that 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 limit equals e to the 0 also equals this up here, because e and the logarithm will cancel. And I like to just write that as we have side work down here, and that tells us by this side work that this limit is e to the 0, which is 1. So if you throw a logarithm on this, you do have to get rid of the logarithm also. Let's look at one more example. I don't know why the board's giving me such a hard time with erasing now. Well, let's look at another example. Which one? Which one's a good one here? Let's see. That one's a little easy. We did a, what was that? That was a 0 to the 0, so let's not do another 0 to the 0. Let's do, I have a bunch of 0 to the 0s. Let's do this one. Example, limit as x approaches infinity of x to the 1 over x. So here, the base as x goes to infinity goes to infinity. The exponent as x goes to infinity goes to 0. So right here we have a limit which is of the form infinity to the, maybe I should have written this up here. This is a 0 to the 0. Right here we have an infinity to the 0. And we can compute this limit by throwing a logarithm on it and then and then applying L'Hopital's rule. So let's do the logarithm work on the side. So we compute, what are we computing? Limit as x goes to infinity of log of x to the 1 over x. Well, that again is going to come out front. The 1 over x is going to come out front. And right here, the way it's written, we now have a 0 times infinity. So we're going to put this 0 in the denominator. And with one like this, it naturally just goes into the denominator because it's already written as a fraction. And you could apply an argument like this where you do 1 over x, but of course that simplifies to just x. Or you could view it as multiplying those fractions together. I view it as multiplying fractions. And how do we compute this limit? Well, as x goes to infinity, the top goes to infinity, the bottom goes to infinity, so we can apply L'Hopital's rule. And that limit is now equal to this limit. Derivative of the top, 1 over x, derivative of the bottom, 1. How does this simplify? Limit as x goes to infinity still, of 1 over x, which equals 0. So this limit down here is 0. That tells us the limit we want is e to the 0, which is 1. So limits like these, I will show you a couple others. And there will be 1 or 2 on the worksheet and 1 on the homework probably. But I will post a couple examples, and you can see in those examples some of these computations could get pretty involved. So the computations we had here, I would say are a little less involved than they can be. But try the ones on the worksheet. It's very important in going through this process to see exactly when you get it into a form on which L'Hopital's rule applies. The ones that get more complicated generally get more complicated after that.